So, we know the statement, we have heard it ad nauseum many times in this course. So, I will not state it. So, the idea is that if you have a continuous symmetry, we should get a bunch of conserved currents depending on how many symmetries are there. Okay. So, the statement of a symmetry is that so prime coordinates are supposed to be the symmetry acts and changes the coordinates from x to x prime. So, this should be equal to, so this is the statement that the action should be invariant. So, this will be a starting point, and so but since we will be very general, we need to even worry about things like does the measure change. Okay. So, let us recall that we will write that the coordinates change as follows. Lambda is our bookkeeping parameter and a mu is some general function of x. Okay. If it were a constant, then it is just plain usual translations, and then of course, d for x prime is equal to d for x. So, first step is we will do is to work out what this measure is. Okay. So, the standard thing is to say that dd plus 1. So, let us write out so this will be the Jacobian, and we need to work out what the change the determinant, or we need to work out the determinant of the Jacobian, because integral dd plus 1 x prime, this measure will be equal to integral dd plus 1 x prime, the Jacobian of, which is the by j of this I mean just the magnitude of this determinant. Okay. So, we need to work out that Okay. Now, this looks very complicated, but what I am going to do is this is only to order lambda square. What I will do is I will use a simple device, which is since this is only to order lambda square, I can take this and write it as exponential of, this is like the identity matrix plus some other matrix, I can write that as an exponential. So, this is equal to e power lambda d nu a mu plus of course errors of the order of lambda square. Okay. And I need to take the det of this. Okay. But now I will use a simple formula which says that det of any matrix is equal to the trace matrix A. Okay. The easy way to see this is to realize that if A is a symmetric matrix, for simplicity, if A is a symmetric matrix, you can always write it as some orthogonal matrix times a diagonal matrix O transpose. Okay. Now, when you go ahead and look at this thing, so what we see is that a determinant of A is equal to determinant of D, and of course, trace of A is also equal to trace of D by using standard properties of determinants and traces. Okay. So, for a diagonal matrix it is easy to check that this is true, and because of this relationship you can see that this is true for any symmetric matrix. For that matter, you can convince yourself that any matrix can be brought to what is called the Jordan canonical form, that this formula continues to hold. Okay. So, I just leave it as an exercise to show this. It is a fun exercise, easy to show for this. Okay. So, now you can see the merit in what I have done out here. I want determinant of e power this matrix, and that just becomes so. So, what we get using this formula as a simple application of this is that the determinant of is equal to e power trace of this thing. Okay. equal to e power lambda. Trace is nothing but, now in this case it is one upper and one lower, so there is no issue, I just say mu mu, okay, that is what I get, plus order lambda square, and this is equal to 1 plus okay. So, I exponentiate and then expand the exponential, because life is a lot easier, because we want only things to first order. Okay. There are other ways of proving this, but I like this method. Okay, so we have taken care of this. So now we just, what I will do is I can write 0 equal to these things, and I just work always to order lambda. So the bookkeeping device is a very nice thing. So we can see that what we get is 0 equal to and since I am going to let me write it out and then explain. Okay. So, so let us for a moment assume that since we are going to work only to order lambda plus order lambda square, since we are going to work only to order lambda square, what I am doing out here is a term like this is already order lambda. Okay. So, if I am going to keep actually I should not have a 1 out here. Okay. So, one term of order lambda comes when this is this contributes a d mu a mu times, then this will be to first order will be just the same as this. So, that is what I have written out here. Okay. But what is delta L? Delta L is the part which actually says forget the take the measures to be the same, to order lambda there should be it should be the difference of these two things. So, delta L is by definition just, I will just write it in short to remind you what it is, instead of writing this is for everything being prime. Okay. It is by L of x prime I mean this object, and L of x I mean this object. Okay. This is just to save space. Okay. But we have already seen something that delta, since L is a scalar, we introduced delta bar of L, which was the change in the functional form. Okay. So, that is not this object, but we had proved something. We had shown that in several lectures ago we had shown something like this. Okay. So, this is what we get, and the advantage of working with delta bar is that commutes with derivatives, spatial derivatives, while this does not. So, this takes care of these things, plus order lambda square of course. Okay. So, now we have a nice formula which has in terms of delta bars and explicit derivatives acting on things, and so we can collect these things and show that 0 equal to okay. So, I am using this formula and plugging it in here, and you can see that this particular term this and this join to give you this term, okay, plus, so this will have a lambda going with it, plus order lambda square. Okay. So, I have just substituted for delta L out here, and that is about it. Okay. So, we can now look at what delta bar of L is. Okay. So, delta bar of L, and L is supposed to be a function of phi, and let us take many scalars, or it could be even a vector field. Okay. So, this will get terms from plus okay, I have done nothing, I have just written out how delta bar acts on these things, and now what I can do is to integrate. So, rewrite this as follows. And then just take this onto this side and write something, and then we will see what we get. So, the most important thing out here is, since we have delta bar here, it commutes with this. Okay. So, I do not have to, I mean, that is the only reason to work with delta bar, is because you have this freedom of what I just did. You can it commutes with derivatives, and so now I can just act on this. I get so, I am writing it as a total derivative plus this object. I am missing something out here. I think it is delta bar of phi a plus this thing. Okay. So far we did not make a, we only used the fact that it was a symmetry, but now I am going to use the fact that this term is 0 modulo the equations of motion. Okay. So, this is equal to modulo equations of motion, because equation of motion is this equal to 0. Okay. So, if I am looking at trajectories which are solutions to the equations of motion, then this will hold. So, it is on a solution. Okay. So, now you can see that delta bar of L can be replaced with this object out here, and just like this was a total was a d mu on something. You can see that the nice good news here is this is also looking like this. So, now you can see that you get 0, which is in of something which is d mu times something. Okay. So, we will get a master formula. That is not yet the current, because there will be several currents, we need details, and so what I will call a master formula is almost the master formula, but not quite. So, I will get 0 okay. And it is not difficult to see that we can argue that the if this is 0 plus order lambda square, now I am dropping that, but to order lambda this term has to be 0, and so what we will argue is that this the integrand is 0, we will argue for something stronger. Okay. So, in other words, this will imply that okay. So, this is what we will call a master formula. Okay. So, what we will do now is to take various examples and extract currents from it. So, the first one to do would be translations, which you have already seen, but nevertheless we can still do it in this setup and we will see. So, we will do 3 examples today. The first one is something which you have already seen, and the other 2 would be new ones. So, the first one is just so under that x mu prime equal to x mu plus, now a mu is a constant, it is not an arbitrary function. Okay. I use the same notation, but I do not think it will be confusing for you. Okay. And how does a scalar field, for a scalar field I do it here, and for a vector field it will be in the assignment you will be receiving later today. Okay. So, this implies that delta of phi a is 0, but delta equal to or delta bar plus okay, because we need in this formula we need to use delta bar. Okay. So, what we get is delta bar of phi a is equal to minus a mu d mu phi a. I will not, I will call this some other index, let us call this okay. So, we have everything, we needed to put delta bar of phi a, which I just worked out, and we know already this thing. Okay. So, we get this, so the master formula, so we plug this into the master formula, and what do we get? We get d mu of a mu L minus excuse me, forgotten. Times delta bar phi a with I put the minus sign here, so I can just pull this out. So, this is what the master formula implies for this. Okay. Now, since a is a constant, I can just pull out this a mu outside. A is a constant, so that it can go through the derivative. So, this is just a mu times d mu times L minus okay, yeah, or I will pull out an a nu rather than this. Okay. So, you can see for every value, for every a there are 4 parameters, I get one conserved current. Okay. And this is what we call T mu nu. So, up to a sign, this is exactly what we wrote. So, this is minus T mu nu, one upper lower. So, I can, if you wish, correct things by lowering this and raising this and writing an eta. Maybe I will write it once. Okay. And this is the object inside the curly braces, which I will call. Okay. This is exactly what we had got earlier. Okay, so now we can see that we have 4 currents or d plus 1 currents if you are in arbitrary dimension. So let us do, so this is the first example. The second one is Lorentz transformations. Okay, so x prime mu nu would be mu nu x mu, but we are only interested to for infinitesimal things, and we saw last lecture that I can rewrite this as okay, and now this lambda itself is my order lambda square. I will not repeat myself. Okay. But again for, so we can see that what we would have called, so this is what I would have called a mu of x. Now unlike this case, it here it is it's a function of x. So it's, so I cannot do things like pull it outside. Okay. So this is obvious. What about delta bar of phi a? This formula will just go through, except a nu should become so a nu d nu of phi a, which should be equal to, now I have to plug in what this gives me. So this is minus lambda, should be a little bit more careful, this mu index becomes nu. So I should call this some other index rho, x rho times, okay. So we just have to be careful to see that the dummy indices do not coincide and things like that. So I have just taken care of that, and so I get delta bar of phi a, and I also know what this is. So all I have to do now is go to the master formula and plug and chug, which is what I will do next. Just a bit of notation here, I am going to follow the convention that my first index is the current index, and this is the nu which came from the parameter. Okay, just remember that. But now what we will see is that our parameters have already 2 indices. So we will have some which will have 3, we will have an index structure of where the current will have 3 indices, 2 coming from the parameters and 1 is the current itself. Okay. So we should be a little bit more careful about how we do things, and we will be. So let us just first step put things into the master formula. The master formula MF. So we have this, so we get d mu of a mu lambda. So a mu we already have it out there, so it is lambda mu nu x nu and minus delta bar of this thing which I have here. Okay. So we are, so now we have to, what we have to do is the analog of what we did here, which is to pull out the parameter. So that is lambdas, but there is some subtlety here. The lambdas, if I pull this down or pull this up, is antisymmetric. So I have to keep the track of that issue. Okay. So let me first do the following, which is to call this dummy index rho for both. Okay. First thing, this is just nothing, I am just renaming dummy indices. Then I will also pull this up, compensate for it by pulling this down. Same thing out here. I have done nothing. I mean, I just relay. I mean, I want to remember that this is antisymmetric. So I pull out lambda nu rho. Okay. So now nu and rho are the 2 parameters associated with the currents. Okay, and how many are there? Because this is antisymmetric, there are d into, so it is d plus 1 into d by 2. Okay, so if you are in 3 plus 1 dimensions, you will have 6 currents, which is exactly what you know. The number of Lorentz transformations are 6. Okay, so I pull out a lambda, so I can rewrite this as lambda nu rho d mu of I have a thing out here. So, delta mu nu x rho, I forgot an L somewhere, yeah, here. Okay. So, this is what I get, but it should be a little bit more. I cannot just erase this, because I have to impose the fact that things have to be antisymmetric under nu rho exchange. So, I have to keep track of that. I do it by explicitly writing this out in this form. Okay. By this, what I mean is, if you give me some tensor which has nu rho index structure, when I write something like this, what I mean is it is T nu rho minus T rho nu. Okay, and there is a similar notation which is to symmetrize.
This comes because the condition is a Lorentz transform.
Yes, yes, yeah. Yeah, since the lambdas are antisymmetric, it follows that only that antisymmetric, the symmetric part of it, of this does not contribute, because symmetric contracted with antisymmetric is not. Okay. So, once I do this, the equation of I mean the current, the conservation law is just this. Okay. You have to write this again in your book, but for me that is about it. Okay. But the caution is that if I did not put this square bracket, that is wrong. I would have more conditions, because it will say, it will give you a d plus 1, it is like a matrix worth of conditions, d plus 1 whole square, which is too many conditions. You got more conditions than parameters in your. Okay, now I do not. If I take nu and rho to be the same, this is 0. The symmetric part is trivially true. Okay. So, now you can see I can define, I can write this whole thing as follows. So, yeah, I can write this as, I like it, I can write this as m mu nu rho. I have to conserve upper and lower indices. There are one upper index in this thing. Okay. But I can also raise it, which is what I will do, or raise both of them. Okay. But if you look at this structure, this looks very I mean it looks like x with going with t. So, let me just write it out, and then we will, I will write a claim which is easy to check. Does this look familiar? Okay, look at the let us look at the charges. Okay, so, this looks exactly. So, let us in particular take mu to be I 0, and then look at. So, yeah, so let us just look at what we would have written for angular momentum in normal this thing. Angular momentum L, okay, would be equal to R cross P. Okay, but if you used, if you wrote out in terms of this, you will see L I or L 1 is equal to x 2 P 3 minus P 3 sorry P minus x 3 P 2. This looks exactly like this. you see there is an x out here and T is like a P. Okay. So, that if I put a 0 out here, so even better. So, let us look at M 0 nu rho will be equal to T 0 nu okay. So, if you think of this as the conserved 4 vector density, then you will see that this looks okay. So, in particular M 0 I j looks exactly like it were right. So, the 0 I j part looks like a normal orbital angular momentum. Okay. So, this object is, but of course, it has other parts to it, nu could be 0 also. So, it is a relativistic generalization of this, and this is called the generalized angular momentum. Okay. Because it has some of its components match our normal angular, what we would have called angular momentum in mechanical systems kind of, and okay. So, that is what we get. Which one? Okay. So, yeah, so this is the current associated. So, yeah, you are right. So, I should call the charges as the generalized angular momentum density, the integral of that over space. So, yeah, so let us do that, let us be more, this is what I should call this thing, and the charges would be, so this is would be, so integral d dx would be the corresponding what you should call generalized angular momentum. Okay. So, it is kind of nice that we see here that this is of the form of r cross p, okay. But what we will see is that that is because we chose our fields to be scalars. So, in your assignment you will be replacing this by the case of electromagnetism, where you have a 4 vector field a mu, and then you will find that you get an extra piece. So, in such cases, so for the vector field or 4 vector field, okay, in your assignment you will see, okay, and we will discuss it for a 4 vector field, for instance. That will have 2 parts, okay. What we will see is that it will consist of 2 parts. One L will be exactly like what I wrote here, r cross p kind of generalization, but then this will not be conserved, the conserved current has an extra piece, okay. So, we call this part is called the spin angular momentum. And this will be called the orbital, the analog of the orbital angular momentum. Okay, it will have 2 parts, and that is it, and there is no. So, now comes the neat thing. So, symmetry tells you that there is a conserved current, and this is that conserved current. You do not have a freedom in this. Okay, we will see that there is some simple freedom which will not change the asymptotic charges. Okay. So, you can modify things, but ignoring such an issue, this is the object which is conserved, and we find that it has 2 parts. Okay. We have not proved it, but you will see it in your this thing, and because of which you see that what you might think is orbital angular momentum is not generically conserved. What you need to include some internal this thing, and this is related to the fact that the 4 vector field a mu has a non trivial transformation law, or let us write it this way. Over and above the transformation of the coordinates, it also has this extra piece which was not there out here. Okay. So, delta bar of a 4 vector. Similarly, if you have a fermionic field which is that will also have a similar term, it will not be exactly this, it will be something else. Key point is that it will have components which will mix under Lorentz transformation. So, even there you will find that there is a spin. Okay. And what we will see is when we go to when you do your course in quantum field theory and you quantize these things, you will see that every field gives you excitations. You will find for instance, if you quantize a vector field, you will get the quanta would be spin 1. Okay. So, so this object will also in quantum mechanics satisfy the same angular momentum algebra that you have, but the fact that it transforms like a vector will tell you that it is something like a spin 1 particle. Okay. I am being a little bit imprecise because most of the time you would have done non-relativistic quantum mechanics, and I am trying to connect up with that. Okay. But we will make things much more precise, part of it in this course and part of it in a course in quantum field theory if and when you do it. Okay. So, what you will see is that this will happen. Okay. So, that leaves us with one example, third example, which will be of an internal symmetry. So, this would be the SON internal symmetry. Okay. So, we already discussed this last time. So, first thing is that x prime mu equal to x mu. So, this implies a mu is 0. Okay. So, in the master formula which I just erased, that first term will not be there. Okay. So, the only thing which should happen is and further delta equal to delta bar, because a mu is 0, there is no distinguish, you need not worry about whether it is delta or delta bar. Okay. So, so we need to, so phi prime a of x will be equal to some rotation matrix which I will write as delta a b plus some antisymmetry matrix a b times this is what we will get. So, this implies that delta of phi a equal to delta bar of phi a equal to, and remember this is again antisymmetric. Okay. So, now in the master formula we just need to, what we have remaining is d mu of delta times delta bar of phi a, but I have it here. Okay. But AAB, and this is a constant matrix, so I can just pull this out, but again like before I need to antisymmetrize with respect to AAB if I am going to eliminate, remove it fully out of here. So, I will just do that. So, what I get, okay, I have antisymmetrized by hand. Okay. So, that I can now just do the simple device of erasing this. Okay. So, how many currents do I get? I get n into n minus 1 currents. So, we will just call this okay. Here upper lower do not mean anything. So, okay. So, we get as many conserved currents as there are independent parameters. Okay. So, let us just take an example. Further example within this, we take n equal to 2. Okay. So, then there is exactly one current. Yeah. Oh, thank you. So, you will have exactly one current. So, we will write that as J mu 1 2, but since there is only one current, I will not write any index. You can just see that this would be okay. Since this only involves derivatives of the field in this thing, you can see only the kinetic energy part will contribute. So, and the Lagrangian was just the normal half d mu phi a d mu phi a minus some u which was invariant, which only depended on that SON invariant combination. So, now you can see that d L by d mu phi 1 will just be d mu upper of phi 1. So, this will imply this is equal to okay. Have you seen this anywhere? Has anybody seen this kind of a current before? Okay. Let me just play a little bit of a trick, convert to complex coordinates. Let us just define let up to some factor. Indices are messed up. Yes, it should be upper. Now we are okay. Yeah. So, up to some factor, this is nothing but maybe 1 over 2 I or something like that. Okay. What would have you seen this kind of a current before? So this is a little bit like the probability current which you have seen in non-relativistic quantum mechanics. It looks like that, right? Okay. So, what we see out here is that this current, so you get a whole bunch of conserved currents, and things are actually a little bit easier when you have internal symmetry. Okay. And I will show you a trick by which we can derive the same current, and this is a nice trick which works only for internal symmetries. For symmetries which act on space time coordinates, it will miss the other piece. Okay. So, it is a fun trick which I use all the time. So, what we did when we were getting these currents was to assume that this the coordinate, these lambdas, where is it? Yeah. So, these were constants, okay, global constants. Okay. So, for Okay. So, I need to define a little bit. I will call a symmetry a transformation is global if the parameters are constants. That is independent of space time coordinates. Okay. So, for instance, that what one would say is that there is a SON global symmetry out here, okay, as opposed to if the parameters depend on space time coordinates then we say that the transformation is local. Okay. In other words, what we have is some symmetry which is acting on some internal space, internal coordinates or internal now quantum numbers, and what is going on is that you in local things at each space time point it has a different rotation. So, here I could just go ahead and write a as a function of x. Okay. So, now of course, if you go back to your action, it is not invariant under local transformations, because we cannot pull it outside this, for instance. Okay. The action is invariant under global transformations, okay. But there is a nice thing which happens. What you do is, if you have a global symmetry, just for fun you say that it depends on space time coordinates, and then you will find a non invariance. So, let us see how that goes. Here I will not use the master formula, but I will just take the action. Okay. So, let us look at this. Okay. I do not need to worry about measure changes, because it does not act on space time coordinates. I just need to consider the Lagrangian. Okay. So, let me do this for, yeah, it does not matter. Okay. So, let us look at how. So, phi a prime was equal to R a b of x. Now, I am making it local. So, it is a rotation which is in internal space, but now question is, how does d mu change? D mu of phi a prime will have two pieces. One would be okay, but the d mu can act on R also now, because it is taken to be a function of x. Okay. If this term were not there, like in a global transformation, then d mu of phi a is transforming in the exactly like this. So, d mu phi a whole square will be invariant, but this will not be, because of precisely this thing. Okay. So, now and what is the term, what is the part of it which is not, first thing is you can see that the potential energy part still continues to hold, even though it is invariant not under just global, under stronger thing which is local transformations, but it is the kinetic energy part. So, we just need to ask how it is not invariant, and again we will do bookkeeping, we will only work to order lambda square. So, let us see what we get. So, so I get pieces. So, I get and just looking at the structure of R A B, this is nothing but you can see that this is equal to d mu of to order lambda square, of course. Okay, so, this is d mu A mu, and so I can write this. Okay, and this is symmetric. So, I can just write this. So, the half out here and I just leave it like this. So, I get this thing. So, now you can see that the coefficient of d mu A B is precisely the current. So, I can rewrite this whole thing as something is messed up. Oh no, it's nothing is messed up. So, we do not worry about upper and lower in this, right. So, times we get exactly what we got here. Okay. So, in fact, you can see in general you can go back and prove that you get exactly the terms which were, I mean this I did for a particular case. For any internal symmetry you can prove that you work to order lambda, and whatever is the coefficient of the non invariance by making a global symmetry into a local one, that gives you the current. Okay. And this is something in practice you use all the time. So, if somebody comes by and gives you some new Lagrangian whatever it is, I just quickly I mean and a new symmetry which you have never seen before, you just do it this way. Okay. But the most important thing to remember is it should be an internal symmetry. Okay. If you try to do it for a symmetry which is not internal, that is acting on space and time coordinates, you get garbage. Okay. So, you can prove that this is equal to the actual thing given by the Noether's master formula. Okay. So, the strategy is the following: if you the master formula is the key thing, whatever is your symmetry, if somebody gives you a symmetry, you have to work out what delta bar of the fields are and just write out what and figure out what A mu is for that transformation, and just put those things in there and just take care that you do not over determine your these things. So, make sure if some parameter is antisymmetric, you antisymmetrize whatever it is the thing. If some parameter is symmetric, you symmetrize the thing, so on and so forth. Okay. So, modulo that thing, you find that you do get a current. Okay. So, this does not require any detail. In the rest of this course, whenever we come across situations like this, we just I will come back and refer to the master formula and say here is the master formula and this is what I would do. Okay.